Good day, judges, mentors, and fellow innovators. We are Team Ikirere Orbital Labs Africa, and today we are very honored to present our innovative project, an AI driven CubeSat safety for Africa. Our vision is bold and is to create a reinforcement learning framework that keeps satellite constellations safe and coordinated, enabling Africa to harness space technology for inclusive growth, resilience, and global cooperation. Why does this matter right now? Space is rapidly becoming crowded, and the risk of collision is rising, threatening global satellite operations. For Africa, the stakes are especially high. Reliable satellite services power critical sectors. To name a few, in agriculture, they provide precision farming and food security. In healthcare, they enable telemedicine and medical logistics. In disaster response, they strengthen early warning systems and coordinate responses. And in connectivity, they bridge the digital divide for rural areas and underserved communities. Without robust automation safety tools, Africa risks losing access to these vital socio-economic services. The challenge is what inspired us to act right now. Now, what is the payoff of safe cooperative constellations? Implementing AI driven safety unlocks three interconnected benefits. The first benefit is the protection of infrastructure, which involves preventing collisions and extending the lifespan of missions, generally what is needed. Now, enabling social economic impact, supporting Earth observation, telemedicine, last mile internet access, building local capacity, developing technical expertise in artificial intelligence and orbital mechanics, and positioning Africa as a leader in space safety research. Our mission ensures that satellites mean secure lives on the ground. Now, what's our solution? We intend for our solution to be a robust, multi layered framework for autonomous coordination of CubeSat swarms in low Earth orbit, or LEO. At its core, it's an RL based coordination system that enables satellites to make real time cooperative maneuver decisions. A safety shield layer acts as a final veto, blocking unsafe and non compliant actions, always with a human in the loop. Finally, a lightweight onboard stack with compressed AI models and inter-satellite communication allowing efficient operations on limited CubeSat software. Together, these elements form a self-learning, self-insured constellation framework. Here, we illustrate how the RL system operates. The CubeSat constellation acts as an environment, generating real-time telemetry and sensor data. The RL agent observes key parameters such as position, velocity, and proximity alerts. It proposes thrust vectors for cooperative maneuvers. But before execution, the safety shield evaluates each command for compliance with orbital fuel and safety constraints. Only filtered validated actions are executed, and feedback reinforces learning for continuous improvement. This loop ensures constant adaptation and high safety standards. Our end-to-end framework takes the AI from simulation to flight readiness. We begin with data collection using public TLEs and synthetic collision scenarios. Next, we integrate the data into realistic GMAT or OrbitKit simulations. We train the model with constrained policy optimization for safe navigation. We apply model compression and quantization to run on limited hardware. Finally, we deploy the lightweight onboard AI for autonomous CubeSat operation. This pipeline ensures efficiency, explainability, and readiness for real-world missions. Our safety shield is the guardian of the system. It applies multi-layer checks across orbital mechanics, fuel constraints, and collision risk assessment. If an RL agent proposes a maneuver that violates mission safety or compliance limits, the shield vetoes it and triggers fallback procedures. This mechanism ensures that autonomy never compromises safety. Our solution stands on four technical pillars. 1. Safe reinforcement learning. This is risk aware algorithms for controlled maneuvers. 2. High fidelity simulation using realistic orbital environments and public data. 3. Model quantization, compression for resource limited CubeSat CPUs. And 4. Explainable decision logs provide transparent, human readable outputs that foster operator trust. These pillars guarantee that our system is reliable, efficient, and accountable. We are a highly specialized and cross disciplinary team. I, Jason Quist, I'm from Ghana. I lead reinforcement learning and machine learning strategy. Gideon Salami, also from Ghana, builds the RL environment and backend systems. Jessica Randall from South Africa applies her mathematical background in machine learning and statistical learning design. Ignatius Balayo from Uganda oversees evaluation and documentation. And Alph Doamekpor from the European Space Agency provides massive technical aerospace expertise and safety compliance. Professor Frank Dagnam overall project guidance and mentorship. Together, we bring the technical depth and coordination this mission demands. Our roadmap covers 5 milestones leading to flight readiness. Month 1 to 3, sandbox simulation with over 95% collision avoidance in test scenarios. Months 4 to 6, stress testing using public TLE data. Months 7 to 9, finalizing CubeSat onboard AI software. Months 10 to 11, lab based test flight with partner institutions. Month 12, we are going to publish results, open source the framework, and release training modules. We conduct regular reviews and advisor feedback sessions to ensure consistent progress. Yeah, with great innovation comes great responsibility, and we do recognize these risks, from aerial instability and data bias to geopolitical sensitivity and dual use misuse. We've built strong safeguards into our framework. Peaceful use and civilian commitment will implement a responsible use policy restricting applications to peaceful civilian missions only, nothing to do with warfare or defense systems. Human in the loop, operators always retain the final go or no go authority. Safety shields, hard coded virtual layers prevent unsafe actions. And on international compliance front, alignment with the ISO 24113 and the United Nations Scopus guidelines. Transparency with confidence metrics. Every decision includes confidence scores and clear reasoning, such as we predicted close approach with satellite B at 300 meters in 20 minutes, 92% confidence. Maneuver required to maintain 1 kilometer separation. Very explainable decisions in natural language that anyone can understand. Equity and inclusion, affordable CubeSats and sandboxes for African labs and universities, regardless of funding. Open source, community centered design, ensuring transparency, accessibility, and collaboration across the continent. These principles ensure ethical, transparent, and equitable process. To transition from simulation to orbit, we see collaboration, partner labs for testing and flight demos, data and orbital advisors for expertise, seed funding and grants for compute resources and infrastructure, strategic advisors for regulatory navigation. Our next step is shuttling our sandbox demo and forming pilot partnerships. In closing, sustainable space operations are not global priority, and Africa deserves a leading role in shaping this future. By merging reinforcement learning, safety shields, and open collaboration, we're building a framework that keeps satellites safe and empowers the entire African continent, forming the base infrastructure for everything that our continent